So we're going to get into photogrammetry a little bit. Pics or didn't happen, right? So photogrammetry is the first remote sensing technology ever developed in which geometric properties about objects are determined from photographic images. Historically, photogrammetry is as old as modern photography itself and can be dated to mid-19th century. In the simplest example, the distance between 2 points which lie on a plane parallel to the photographic image plane can be determined by measuring their distance on the image if the scale of the image is known. There will be some material reviewed in this lecture based on what you guys learned about scale in the previous modules. The focal length of a lens is an optical property of the lens. It measures the distance in millimeters between the optical center of the lens and the camera's sensor, or film plane. It is determined with the camera focused to infinity. Lenses are named by their focal length, and you could find this information on the barrel of the lens and sometimes on the aerial image itself. For example, a 50 millimeter lens has a focal length of 50 millimeters. Compare the scale of an image and the scale of the object. The ratio between them is the same as the ratio between the distance d and the focal length f. Therefore, the ratio between the size of a pixel on the image sensor and the size of a pixel on the object is also the same ratio. Airborne film cameras have been in use for decades. Black and white or panchromatic, natural color, and false color infrared aerial film can be chosen based on the intended use of the imagery. Panchromatic provides the sharpest detail for precision mapping. Natural color is the most popular for interpretation and general viewing. Color infrared is used for environmental applications. The most important geometric properties of an aerial photograph are those of an angle and scale. The angle at which an aerial photograph is taken is used to classify the photograph into one of three types: high oblique, low oblique, and vertical. Vertical photographs are taken with a single lens, and it is the most common type of aerial photography used in remote sensing applications. Truly vertical aerial photographs are hard to obtain because of unavoidable angular rotations or tilts caused by the angular altitude of the aircraft at the time of exposure. Vertical photographs have properties similar to maps with an approximately constant scale over the whole photograph, so they can be used for mapping and measurements. There are a few identifying features that we need to take note of to gain information about what and where we are looking at. We have fiducial marks, which are silhouettes at the edges and corners of the photograph. Principal point, lines that connect the opposite pairs of fiducial marks to find principal points, which is the optical center. The ground nadir, a point on the ground beneath the center of the camera lens at the time of the photograph was taken, and relief displacement, the effect you see of increasing heights of objects as distance increases from the nadir. Some aerial photographs are going to have more information than others. So if we take a look at this photograph here, we can find a few things. So first of all, we have our flying height, which is displayed here, or our altitude. We have the project number and name right here. We have our fiducial marks, which we can normally see on an aerial photograph. This is a little bit small, but once this is in PDF form, you can zoom in on it a little bit. We have the lens serial number for the camera. We have the negative number of that negative slide. We have the focal length here. And of course the time that the photo was taken. So here we can see a basic example of these aerial photo features, and you could still determine the principal point by using the fiducial marks. So here we could see the fiducial marks on this aerial image all around. And if we were to cross all of our fiducial marks together, that is going to give us our principal point right in the middle. And so that is exactly where the camera was above during the acquisition of this photo. So we want to, sometimes we have to identify the frame number, and you can identify the flight path. You will also need to know what you're looking at to orient yourself to determine that flight path. So when you get a series of aerial photographs, you want to know whether it's going north to south, east to west, etc. And so we use this information for sequencing images along the flight path. So what I want to look at here is we have our frame number. So we have 20 and we have 19. So we need to know which direction it's going. So this is an image from Google Maps, which displays Cape Kennedy. And so now I know that I'm oriented from north to south. So if I go back to these two images, I can now easily tell that I'm going from north to south here. From just Googling that image, I can orient myself a little bit better. Okay, so terrain variation, which are the differences in elevation within an image area, is often the largest source of geometric distortion in aerial images. Terrain variation causes relief displacement, which is defined as the radial displacement of objects that are at different elevations. So depending on what angle the camera is placed, whether it's balanced, where the aircraft is on a flight path, can all be causes of relief displacement. So if you're right above a building, you'll get that straight on look. If you're at any other angle, you're going to get that relief displacement. So this is a little bit of review. Ground distance equals measured distance, denominator of the scale, which is the number after the colon. If you have a scale of 1 to 25,000, one map unit equals 25,000 ground units. So to determine the length of an object, you would take the known scale. So again, this is mostly review for you guys from our scale section. You can also calculate solar elevation on the NOAA solar calculator, but you need to know the exact day and time to do so. You can find this information on the aerial photo most of the time as well. So if we want to figure out the height of an object in the photo, we would have to know the height. We would need to measure the shadow on the photo, and then we would also need to know the solar elevation or altitude of the angle, which again you could look up on the NOAA solar calculator. You can also determine flying height, and you can calculate flying height by knowing the scale, flying height at sea level, and the average elevation of the terrain above sea level. So again, you just have your basic formulas to determine different information for these aerial images. And as long as you can figure out all of the portions of your formula, or at least most of them, you could solve for any of these.